To backtrack a couple slides, this is a fairly complicated chapter. There's a lot to learn, so if you missed it on the first half of this lecture, it's going to be pretty tough. Make sure you go back and read it all. Watch lectures that may be available. You might be able to buy those in the bookstore still. I've been talking about Lewis structure, how we can take the number of valence electrons of something and give it a structure, position atoms next to each other, and figure out how they're going to orient themselves, figure out how they're going to connect to each other, and then whatever valence electrons are not involved in bonding, we'll be able to label those and we'll be able to see those. I went through some fairly straightforward examples in class, because what that lends itself to ultimately is us being able to then take what we get on paper in terms of how atoms are spread apart and how they orient themselves, take that and then build a three-dimensional model so that we can understand that in real space how it would move, how it would interact, and what areas it would have on it. Few of the shapes that we talked about already. Remember, I had the model that we were talking about. One of the shapes was a linear shape that could occur, and a linear shape would happen if these weren't here, for example, and this was just flat. You would have an atom in the middle with two things on both sides of it. The bond angle would be 180 degrees. Remember, the bond angle is this angle right here between these subsequent bonds right here. When you stretch all that out, that's 180 degrees. That would be a linear shape. What you have here is, remember I talked about the valence shell electron pair repulsion theory, the Vesper theory. Vesper theory states that whenever you have chemical bonds, what will happen is these areas, these springs again, represent shared pairs of electrons between atoms. What will happen is that these guys will spread themselves as far apart as possible because like charges repel each other. Opposite charges attract, like charges repel. They will move as far apart as possible, and that's how come in 3 dimensions you get a different bond angle than what you would get in 2 dimensions like on your paper. If you just wrote down an atom in the center with 4 things around it on your paper and spread them out as far as you could, the farthest you could get them would be right angles, right, from one another. But in reality, in 3D, whenever you let it poke out towards you and away from you, not just flat on the paper, you can actually end up with an even farther distance, an angle greater than 90. And this would be, do you remember what the angle would this, for those that were here? Good, 109.5 would be this angle right here. Okay, that's the angle for a tetrahedral. All right, well, we got linear, 180-degree bond angles. We've also got the trigonal shapes that we talked about, one of which was trigonal planar. In that case, remember what I said about when you have a plane, you would have a trigonal for the fact it's got 3 sides, obviously. Looks like a triangle. But trigonal planar is a little bit different than the other one. We also learned about what's called trigonal pyramidal. Trigonal planar is whenever you could imagine this molecule just like you would have drawn it on the paper, and in real life, if you would pick it up and set it down, all of them, like if you set it on a table, all of those would touch the table. None were setting up higher than the other. They were all on the same plane. Okay, they were all flat, sticking out. Then if it ever sticks up like this, like the middle one is a little bit higher up, it's more 3-dimension. Instead of being in one plane, we call this trigonal pyramidal. Okay? All right, so the trigonal shapes, we've got 3 areas around 3 areas of electrons around a central atom, like you see here. Now, if it's just flat, if it's trigonal planar, the farthest apart these things can get from each other in terms of a bond angle is 120 degrees, right? Because 360 degrees is all the way around. So split it in thirds, 120 degrees. Now, if all of these are bonding, if these 3 groups, I want you to think about what I said in class. If I'm looking at one central atom with 3 things sticking off of it, let's say all of these electron areas were involved in bonding, like you see here. So you would have atom, atom, atom. We can see atoms. We don't see electrons, but we see atoms. So if all these were actually involved in bonding, you would see all of these atoms present. The shape that you would get is called trigonal planar, and the bond angle would be 120 degrees. However, what if 2 of the groups were bonding, and one of them were actually a lone pair that were not involved in bonding, how would this change the shape of my molecule? Well, non-bonding, if it's a lone pair, that means you don't see this atom. There's no atom there. It's just got electrons buzzing around the top of it, we'll say. Okay? Now, those are valence electrons, but they're not bonding with anything, so we don't see them. But they are still there, and they are exerting their force to try to separate things out apart from each other. Okay? So, realize everything else stays the same. It's just you don't see this guy up here because it's a non-bonding pair. So what would this look like? That's not trigonal planar anymore. We call that bent. Okay? Because all you see is it looks like it starts out here, goes up, goes back down. Okay? We've got a bent molecule. Realize, though, that the reason that you have a bent molecule in this case is because these electrons are still here, and they are exerting their repulsive force as if there was a bond here. Okay? That's why this can end up with a bent. So it takes a little abstract thought. We've got to think about this. Then we had our tetrahedral shapes. Now, a tetrahedral, again, is when all four come out from a central atom. And it sort of looks, imagine it's like a pyramid with the points there, but without the sides on it, right? I could put a side here, a side here, a side here, and a side on the bottom, and it would look like a little pyramid if I closed it all in. I have 4 points, 4 corners in space, all occupied, from all the atoms coming out from the center. This is called a tetrahedral shape. Okay? 109.5 degree bond angle. All right. However, you can imagine now that this is going to look different if all of these are not involved in bonding, right? If this electron pair, for example, was a lone pair and not a bonding pair, but it was still there, exerting a repulsive force, what that means is I won't see this. Okay, so I'll just pull this off, but realize there's electrons here exerting their force. So this looks now different. Remember what we call this shape? Trigonal pyramidal. This is trigonal pyramidal, not trigonal planar. What's the difference? It's sticking up in the air versus laying down flat all the way. That would be planar. This is pyramidal. It's more like a pyramid. Okay? So, the only way you're going to get this shape is if there's something above, right here, exerting a downward force to push these guys down farther away from each other. Right? So that would be the case if the electron geometry was like this. Okay? There's a difference between what's called the electron geometry and the molecular geometry. One is how the electrons are sitting. The other one is what do you see as a result of that. Okay? So in this case, what would happen is, take a look here. This would be tetrahedral shape, right? What I would say is, okay, according to my electron groups, how are they arranged? What shape would my electron groups be shaped in? You would say tetrahedral, right? The molecular geometry, what does my molecule actually look like? The parts that I can see, tetrahedral, right? Now if I do this, I don't see anything up here now. So my molecular geometry, what I actually see is trigonal pyramidal. Okay? However, if I asked you the question more specifically and I said, what is the electron geometry for this? The electron geometry is still tetrahedral. Okay? Because that's what's governing this whole shape right here. So the electron geometry, the way the electrons are distributed, is tetrahedral. The shape, the molecular geometry, what I would actually see if I were looking at the molecule, is trigonal pyramidal. Right? So, review again. What's the electron geometry for this? What's the electron geometry? Tetrahedral. What is the molecular geometry? Tetrahedral. Let's try this one. What is the electron geometry? Huh? Tetrahedral. What's my molecular geometry? Bent. Good. See how that works. There's a difference. There's 2 terms we look at here. Electron geometry and molecular geometry. Okay? All right. That's what I just went through right here. Okay. So, this explains something. Okay? Water is H2O. If you sketch the Lewis structure for water, what you will get is, you will get O in the center, right? You will have H on both sides. You will connect them with a line on your paper. Then you count up how many valence electrons. I went through this in class, how to come up with a Lewis structure. You count up how many valence electrons each brings to the table. Oxygen will bring 6. Each hydrogen will bring 2. So that's 10 total electrons. 8 total electrons that you have to deal with, right? Do what? What did I say? Did I say it wrong? You're right. I was wrong. That's why the math wasn't adding up in my head. Oxygen brings 6. Each hydrogen brings 1 valence electron. Thank you. That means you've got a total of 8 that you have to deal with in your structure, right? All right, so remember what I said. The first thing you want to do is, now that you know how many valence electrons you have to deal with, look at how many you've already burnt, just connecting them together. Remember that each one of the lines, like springs up here on this model, each line represents 2 electrons because that's a shared pair. So already, with oxygen, 2, 4, you've lost 4 of them. Okay, you've got 4 more you have to account for. So you start on the outside and you fill it in until you get to the inside around the outsides of these atoms with your dots. Well, you can't add any more with hydrogen, right? Because it's already full. It's already got 2. So there's only one other place you can put these electrons, and that's above, just on your paper, you'd probably have it like above and below your oxygen, right? Because you wouldn't put 4 up the top. I told you when you're writing Lewis structures, treat it like a square, put 2 on each side or whatever. Doesn't really matter all that much. Just realize you got 4 electrons that you're going to have to attribute to oxygen now. Count them up, 2, 4, 2, 4, 6, 8. All the electrons are there on your paper. You've accounted for, you've got the Lewis structure for water. So what you've got is an oxygen with a hydrogen on both sides, 2 dots, we'll say 2 dots above the O and 2 dots below the O. That's what your Lewis structure would look like. Okay? However, in real life, that is not an accurate representation of what water would look like in 3 dimensions. On your paper, it probably looks like that you have water as a linear molecule on your paper. You would have your O in the middle and your H on both sides, and then you have your dots drawn, right? In reality, though, water looks like this. It is not linear. It is bent. Why is it bent? You tell me. Because of those lone pairs of electrons that are still there, okay, above and below the oxygen. It's like we go back to this now. We go back to the fact that you got to consider in a tetrahedral type of shape, there are 4 corners in space for these molecules that we're dealing with, right? In the case of water, 2 of them are taken up by hydrogen atoms, but in the case of the oxygen here on the water, you've got, just like 2 springs coming out of it, you've actually got 2 sets of electrons. It should be open. They can just open the door. You've got 2 sets above and below, right? You got these 2 that are not involved in the bonding. You've got these 2 that are not involved in the bonding down here. So you get this. And when they all spread out from each other, look what has to happen. You have to end up with a bent molecule as opposed to a linear molecule. Okay? So that's why we have to know the difference. We need Lewis structures to come up with the general distribution, but we need to be able to then incorporate repulsion theory and 3-dimensional thinking so that we can figure out what the actual shape of these things will be. Okay. Same thing with ammonia. If you have ammonia and you draw it on your paper, you'll get the Lewis structure for this. Okay? You'd probably draw it like you would see there. But what would it actually look like in 3 dimensions? If you had an N in the middle, 3 H's on it, what you got to realize is that with that N, you've also got a lone pair of electrons, like you see here. So that means it's not going to be flat and trigonal planar, like it would look like on your paper maybe. It would actually, those electrons would be exerting repulsive force, and it would be just like you had something else attached up here. They would all spread out, and you would have a trigonal pyramidal shape for an ammonia molecule. Okay? The center would be a little bit above the things coming off of it. It's down here. So we got to think about 3D. All right, I've already went through all of this. So in a linear geometry, again, just to reiterate, you're going to have 2 electron groups. Remember, an electron group doesn't necessarily mean a single bond. It can mean a single bond, a double bond, a triple bond. It just means an area like this that we're going to call a group. It's got something coming off the central atom. So we've got 2 electron groups here. They're both bonding groups with no lone pairs. that means that these guys are going to want to spread apart from each other as far as possible. That's how come you get this linear shape. That's why CO2, for example, is a linear shape. Anytime you start having unshared pairs, lone pairs, anywhere around the central atom, it's going to affect your shape. Okay? It's going to change. It's going to exert repulsion and affect the bond angles here. So the electron geometry is linear. The molecular geometry, when you actually look at it, the angle is 180. When you actually look at it, it also will be called linear. Okay? All right. Just to reiterate again, if you have a central atom here, and you got three things sticking off of it, notice that there are no lone pairs here affecting the shape. So what you're going to want to do is evenly distribute all of those areas. Okay? When you spread them all out, like you see here, that means you're going to end up with about 120 degrees for your bond angle. Three bonding groups, no lone pairs. Your electron geometry, how the electrons are distributed, trigonal planar. It just so happens that when we look at it, our molecular geometry is also trigonal planar. For bent, here you've got three. You end up having three total, at least three total bonding areas. You've got 1, 2, 3. You could actually have another one down here, like in the case of water. But the point is, you've got more than just two areas here. You've got at least three because of what's going on with the central atom. Okay? So what's going to happen is, when you look at what's going on, these are not. They're going to want to spread apart from each other. But if you just focused on these lines and looked at those and see how far they were spread from each other, you haven't separated yourself fully as far as you can from these other two that were up here on your structure. So you want to spread them all out. And when you do, you get something like this. You end up with a bent structure. Okay, so your electron geometry is actually trigonal planar. And since we've got, this is just a lone pair, you're not actually got anything hooked to that. This looks bent. This is not trigonal planar. It's a bent molecule, even though the electron would be trigonal planar, the electron geometry. All right. Here's methane, carbon, 4 hydrogens like I've got up here. 4 bonding groups here. They're going to spread apart as far as possible, but you got some going back that way, this way, coming at you, going up, spreading out in 3 dimensions so you can get more than a 90-degree separation. No lone pairs. You're going to have a tetrahedral electron geometry as well as an actual tetrahedral shape that you're looking at with all atoms involved. Okay, if you have, however, this type of situation as your Lewis structure, as we went over a second ago, this is going to affect your bond angle, right? So instead of being just trigonal pyramidal trigonal planar and all spreading out, all flat together, this is going to want to try to push things out of the way as well. So it's going to be as if you had another bond up here sticking to something else. You're just not going to see that thing, that's all. So when they spread out, it's going to be like tetrahedral minus one of the corners is what's going to happen. Okay? So you can imagine, like on the last picture, you saw a bond right here. That's not there anymore. But there are electrons there that are exhibiting the same type of repulsive force as if there was. So with ammonia, these 3 bonding groups with 1 lone pair, you get an electron geometry of tetrahedral. The way it would work out if everything was there, if this was sucked up, we would have tetrahedral. But we don't, because when we actually look at it, our molecular geometry is trigonal pyramidal. Okay? Questions about that? Same thing with bent. Okay, you can see how it all works out. You have to think about this. I'll have questions like this on the test. All right. Now, moving on from that, we have another concept that we have to consider that we cannot answer until we are able to come up with these 3-dimensional structures of things. Now, once we've done this, we can take now a molecule and try to figure out how it's going to behave, because we're going to look at what the bonds are. Is that central atom a carbon? If so, what are the terminal atoms? Is it a halogen? Is it another hydrogen? What is it? And depending on what it is, it's going to affect the strain and the pull and the tug that's going on this atom, or on these atoms in this molecule. And that pull and that tug gives that molecule different properties, and it'll affect the way that it behaves. This brings us to what's called bond polarity. Just summarize it. Polar. If something, well, think of like bipolar and what it would mean and the characteristics of that. Polar means two opposite ends. Okay, like a magnet has a north and a south end. Our Earth has a north pole and a south pole. They are two identifiable and different areas with different characteristics. Okay, they are easily located. You can look at a place and say, there's point A and there's point B, and they are identifiably different from each other. So something becomes polar at that point. In bonds, this becomes very important, okay? Because on the periodic table, some things really like to take electrons away from other things. Other things really are weak, and they really like to give up electrons in order to get themselves happy. Whenever this happens, it then becomes very important, or knowing that this happens, it becomes very important to know what's going to happen when you stick two things together. Who's going to be pulling harder on these electrons, and will that have any difference on how this atom is going to, or this molecule is going to behave? Okay, so just like in real life, everyone's of a slightly different strength. So if we all pull on something, there's no way, unless we are an exact clone of ourselves, when we put something on both sides of a rope, let's say, and try to tug it and pull it, unless we are exactly the same person on both sides, there will not be a perfect, even tug on both sides. There will always be a situation, just like in chemistry, when you put two things, and instead of pulling on a rope, it's a bond that exists between them. One side's always going to be pulling a little bit harder than the other side. Okay? All right, so you get unequal sharing of the electrons is what happens. Just because they are sharing, just because sulfur and oxygen end up sharing electrons, don't for a moment think that they're both happy about it. They are, because it satisfies their noble gas configuration. However, don't assume that it's hands down the most ideal thing that they would like to be doing right now. What happens is, whenever you put sulfur and oxygen together, for example, yes, they will share electrons amongst themselves to form that covalent bonds that they need. However, in that case, what happens is oxygen actually is a little tougher, is a little stronger than what sulfur is, and it will actually pull the electrons towards itself a little bit more. Now, sulfur still has the ability to get them when it needs it, but they'll actually move closer and spend more time with the oxygen than the sulfur. It's just life. It's just as unfair for atoms as it is for everybody else. What that results in is something that you see like down here. For example, if you have hydrogen and chlorine together to form hydrochloric acid, they will come together and they will have two electrons that they are sharing as a pair. Okay? So there's this overlapping orbitals right here, and you're going to have two electrons being shared between these guys. But the difference is hydrogen is a measly little atom, and it does not have the strength to pull very hard electrons towards itself. Chlorine, on the other hand, is really good, is strong, and likes to pull electrons towards itself. Now, sometimes what happens is when you put two things together, the difference in strength is so great that one completely is able to dominate the other one. And when that happens, such as a metal and a nonmetal, you get a situation where, like, sodium comes up, chlorine comes up, and chlorine will actually take that electron. There's no sharing anymore. The pull is too great. The chlorine will take that electron, take it to itself, leave sodium without its electron, have a chlorine now that has gained an electron entirely for itself, and that creates an ionic bond. Okay, that's how this Na positive Cl negative stuff. We've talked about that. We talked about how sodium wants to give that up anyways. Don't feel bad for sodium. Don't feel sorry for sodium, because sodium is actually happy. By giving up and by letting chlorine have that electron, it in itself now becomes more stable. And it achieves a noble gas configuration. It can achieve a configuration that makes it more stable. Chlorine does the same thing when it takes it. So now you've got a give and take. However, when you make the fight more fair, and you put two people together, two atoms together, that are closer together in strength, sometimes one can't win over the other. Sometimes you have to just call it a draw. It's kind of like in real tug-of-war, right? You know that in real tug-of-war, there's two lines on the end. If we put everybody up, we split the class in half, put half of you over here, half of you over here. We started with the flag in the middle, realized that for this team to win, you got to pull that flag all the way over there. It could be several feet before you can cross that line, right? Same way with the other side. As long as that flag is anywhere in between those marks, nobody wins, right? I mean, this team over here, if the edge was the table, you had to pull it past the table. This team over here could pull this all the way over here and get this far away from the winning line, but unless they ever cross it, they don't win. The same thing can happen with atoms. Just because it's a very lopsided sharing, one atom could be pulling so much harder than the other, but hasn't really broke that definition to where we can say it's separated it out. It hasn't pulled it out for itself yet, but it's very lopsided. Okay, so the closer things are in strength, the more that flag stays in the middle with that tug of war game, right? Same thing with the atoms. The closer these two are in strength, the more evenly shared these electrons are. When one starts to gain a little strength over the other, a different bond exists where there's different strength. You get a lopsided sharing. If that lopsidedness gets big enough, you actually get a winner. Someone takes the electrons. So you can see now why ionic bonding, which is what happens whenever someone loses and someone wins, ionic bonding is a far weaker bond than a covalent bond. They've actually been already separated out. The electron's already traveled and it's moved. And the only thing holding it together is the positive-negative attraction that exists between that types of matter. In a covalent bond, everything's sort of stuck together. It's all balanced out. All right. Now, this little funky symbol that you see down here means partial positive and partial negative. What that means is that when you have something that is really, really good at pulling electrons towards itself and something that's not very good at it, and you can look at this molecule and see a shift in electrons towards that way. They've not pulled it off completely, but you can see a bigger density in one area where the electrons seem to be where there's more. We give that a partial negative indication. That's how we identify polarity. We have a partial positive end and a partial negative end. Now that's not positive and negative. The only time you get positive negative is whenever one completely loses and one wins, and you get an ionic bond. This is not what this is. This just allows you to show where the more negative place is because of where the electrons are, and the more positive place is because that's where they tend to spend less time. Okay? Now this plays out in chemistry because when you have polar compounds, things like water is polar. If you draw the structure for water, the O is in the middle and the H is on the side. What you will see is as oxygen, like this chlorine, likes to pull those electrons that it's sharing towards itself. So that the oxygen area on water actually has a little bit of a partial negativity associated with it. The hydrogen areas on water has a little bit of a partial positive associated with it. So what happens is, whenever it's almost like charges. They sort of act like charges, but they're not real charges. Whenever you drop something in, like salt, for example, that's very ionic and has very distinct positive negatives whenever the sodium and the chloride separate, water can pull it apart very easily because the negative area on water can stick with the positive sodium ions and pull it apart from the crystal. The chloride part, the hydrogen part of water that's positively charged, sort of, can grab on or separate out the chloride part of your salt because positive and negatives attract, right? So it can help spread it out. So since water is polar, it dissolves ionic things and other polar things very well. However, as you will see a little bit later in another chapter, there's a reason why, for example, oil and water don't mix. And it has everything to do with polarity of the molecules involved. The only way that you can dissolve something is to know whether or not it is polar or nonpolar. If it is polar, and you have something else that's polar, you can use it to dissolve it because there's areas that will be attracted to each other. If you have something that's nonpolar, and you try to dissolve it in something that's polar, realize that something that's polar, if I put in something that's nonpolar here that doesn't have those regions, there's nothing for it to grab onto. There's nothing for it to be attracted to, so it won't spread it apart. It won't dissolve it. Okay? We'll talk about that a little bit later. But we start understanding a little bit more of this. So we have bond polarity. Okay, so when I was talking about that strength, how some are stronger than others and have the ability to pull electrons towards themselves, that has a name. The name is called electronegativity. If something is highly electronegative, it has that want and that ability to pull electrons towards itself. The most electronegative atom would actually be the fluorine atom that you see up here. The next best thing that plays out in our life, because it doesn't form an acid like fluorine would, is oxygen. Oxygen is a great electron acceptor, electron stealer. There's a reason that in our body we use oxygen. We have to have, for those that have to take anatomy and you learn about cellular respiration and the mitochondria and what happens in the mitochondria, oxygen has to come into our bloodstream and go there. And the reason is because when we make ATP in our body, in our mitochondria, one of the things that happens is there's some chemical reactions that involve hydrogen in that area, and the electrons get pulled off. The electron that hydrogen has gets pulled off, and a whole bunch of them get pulled off from subsequent hydrogens. And you got this little chain called the electron transport chain, if you remember. This little chain of electrons that gets moving through your mitochondria membrane. Something has to be there like a sponge to soak up those electrons, because if it's not, bad things happen. Our cell starts to undergo reactions, things fall apart, and things stop working. That's why oxygen goes into our body. Oxygen is really good at being an electron sponge. It'll go in there and it'll soak up those electrons. And when it does, O2, gaseous oxygen, becomes electrically charged. At that point, it becomes an ion. And when it becomes an ion, it becomes reactive, and it reacts with whatever's around it. In most abundance around it is water, is hydrogen that comes from the water. So when oxygen is there, it'll react with hydrogen that's there and form more water. We breathe out water vapor, and we breathe out carbon dioxide. Carbon dioxide, you learn where it comes from. It's in the Krebs cycle, where we make that. But the reason that we breathe out water vapor is because of that reaction with water, with oxygen, to make water, because it accepts electrons. So electronegativity, how much it has pull, how much it wants to take in electrons. Okay? Now, as far as how you can predict which one is going to be more electronegative, here's the way the table works. Okay, this is in your notes. I'll have this version probably on the test, but they tell you the same thing. One's just more artistic than the other. The way it works is as you go over and as you go up. So in other words, as you meet towards the top right of the table, excluding the noble gases here, the more electronegative you become. So notice that fluorine is a 4.0 relative value. It's the highest one up there. It's very electronegative. Oxygen's a close second. It's 3.5. It's very electronegative. Notice this guy down here. You get down to francium, 0.7. Remember, those are metals that really like to lose their electrons. So remember metallicity? On the last lecture I talked about how do you determine which is more metallic than the other. We said down and to the left is more metallic. It makes sense that the more metallic you are, the more you want to lose your electrons, because that's what metals do. They give up electrons to help fulfill their most stable electron configuration. So this guy down here really likes to give up electrons. It makes sense. So it's very much not electronegative. That very much is electronegative. Okay? So when you put something like oxygen and francium next to each other, that's not a fun fight to watch. It's sort of like those. Anybody watch Ultimate Fighting? You get on that and you're like, oh, this is going to be an awesome fight, and then a couple punches and it's over, then that's it. And then you paid all that money for nothing. Now you don't have to pay for it. You can watch it. But back when it first came on, it was all pay-per-view, right? So it's kind of like that the Holyfield-Tyson fight, when he bit off his ear. It lasted no time whatsoever. And I was in a house up in Indy, and there was a bunch of guys that were watching it, and you paid the money for it, and then it was over. It was nothing. It's like, man, $50 for nothing. Or however much it was. I don't know. All right. Let me make sure on that one slide, I think there was something I was going to say. Oh, I know what it was. What we can actually do, why these numbers are important, is because sometimes it's hard. Because, for example, what if I said aluminum and phosphorus? They're kind of close together, right? How do I know the tipping point? How do I know when it's no longer just trying to share versus somebody wins? Well, there's number values that we can use to answer that question. That's why these numbers become important. What we'll want to do is take the difference in their electronegativities. We'll subtract the difference. So we'll take, whichever one's bigger. Phosphorus is 2.1, aluminum is 1.5. You subtract those, and then you see where it falls on a scale, and then you can determine what type of bond that is. Is that one that's going to be shared pretty well, or is that one that's going to be lopsided, someone's going to win, or whatever? So these values will be useful to you. If we have a situation for example, where I have, let's say, 2 chlorine atoms, and I put them together, that's not going to, you know, that's not really a fun one to watch either, because it's going to go on forever indefinitely and no one's going to win. Because what happens is you got chlorine and you got chlorine, you got the exact same thing with the exact same strength. So when you put them together, they're just stuck there and they're pulling and nothing moves hardly. Okay? In that case, whatever value chlorine is, let's look. Chlorine is a 3.0, right? What's the difference in their electronegativities if you have 2 chlorine? Well, the difference is 0, right? You got 3.0 minus 3.0, that's 0. They're the same. There's no difference between them, so they're pulling with the same strength. If you have that situation, such as what you would have with your diatomic molecules, NOF, Cl, Br, and I, how they all form 2s, right? I2, Br2, and H, H2. When you have those together, you've got that. You've got 2 things pulling with equal strength. The difference between their pulls is 0. If you have that, you have what's called a pure covalent bond. A pure covalent bond because nothing's lopsided and they're sharing. Now, what if you fall within this range? If the difference is very small, it's only from about 0.1, anywhere from around 0.1 to 0.3 in that area. Then you would have what's called a nonpolar covalent bond. You would still, it's almost like if you're looking at it, you still would see everything balanced out. But if you looked close enough, you would see there is a little bit of an advantage one way or the other. One's pulling a little bit more, but we can't call it a pure covalent bond. And the reason is because it's not pure. It doesn't represent perfect balance. The only way we can get that perfect balance is if we have 2 of the exact same thing pulling on each other. Okay? So, but if it's really close, but they're not exactly the same thing, then you're going to have what's called a nonpolar covalent bond. It's nonpolar because, remember, polarity means very lopsided. Positive end versus a negative end starting to appear. That's not going to happen in this because no one's pulling hard enough. Now, however, if you take the difference between them and you start getting a little bit higher, there's a bigger difference, somewhere between 0.4 and 1.9 difference. Then you're starting to get, you've still got sharing, but it's sort of like that game of tug of war where you're starting to get far closer to one side than the other. In that case, you have what's called a polar covalent bond. They're still sharing, nobody wins, but it's starting to get lopsided. You can start seeing polarized regions in this molecule. Then once you get past 2.0, okay, if it's larger than or equal to 2.0, that means that's the point where you say someone has won. It's ionic now. Someone actually took the electron, someone actually lost the electron is what happened. So I'll give you this scale. I'll give you the table with electronegativity values, and I'll give you this scale. And you're going to have to be able to look at things and interpret them and tell me what type of bond will form if these 2 things stick together. So here would be like 2 Cls for pure covalent. You could still have another covalent here with H and F, but what you would have here is a difference of 1.9, so you're going to end up with the polar side of things, right? It's going to be a polar covalent bond. Ionic means that, notice how the sizes start to shift, right? Here, they were sort of all blended together. Here, it's more around the F. Here, they've actually closed off from each other. It's completely separated, like in NaCl. You've got an ionic compound, ionic bond. Okay, so these little things that I showed you, this little partial negative, partial positive, at any given point, if that exists in time for an atom, or for 2 atoms next to each other, or whatever, for a bond, we call this a dipole moment. A moment that exists in this molecule where there are 2 poles. So that hence the word dipole. Okay? So a dipole moment is any material that you have that has positive and negatively charged ends, like we see right here. Okay? It's a dipole moment. I already said this. So a polar bond is going to have a partial positive area and a partial negative area. They're not full charges. They're not real, like, that's why we had that little sign in front of them, but they sort of act like it because of the way the electrons are distributed. Don't worry about this. Okay, now what's the point of all of this? The point is to now look at that table, to understand what polarity means, to be able to take our Lewis structures, see how it all ties together. You have to know your electron configurations so that you can write a Lewis structure for something, because you have to know valence electrons. Once you know the Lewis structure, you can predict the molecular geometry, 3-dimensional shape. once you know the three-dimensional shape and you know what type of bond you are dealing with, like if I have carbon with 4 hydrogens, I want to look at this carbon and this hydrogen and who's pulling who the hardest. And if I look at that in all areas, I can start looking at how the pull is distributed all the way throughout this molecule. And when I look at how that pull is distributed all the way throughout the molecule, I can start looking at and understanding why the molecule does the things that it does. Why does it have a lopsided end on altogether versus a non-lopsided end, and how is that going to spin through space, and how is it going to react with other things? So we have to put it all together. Polarity is going to affect, I'll talk about this in a second, so don't worry about that. Polarity is going to affect the intermolecular forces. Big words, what does that mean? Inter means between, right? Molecular, you know what molecules are. Intermolecular forces are forces that exist between separate molecules. For example, if I have a water right here, it's bent. Imagine it being bent with an oxygen in the middle, with 2 electrons above and 2 electrons below, right? And I've got hydrogens on both ends of that oxygen. And I got 2 of these, and they're spinning around, flipping through space like they really do. What happens is, where that oxygen is, it's pulling the electrons from this hydrogen a little closer towards the center where that oxygen is. It's pulling the electrons from this hydrogen a little closer to the center where the oxygen is. So I've got these molecules spinning around in space with a partial negative region around the oxygen and partial positive regions around the hydrogen. Okay? So as they spin around, guess what? When 2 molecules bump together, the hydrogen part that's partial positive and the oxygen part over here that's partial negative can orient themselves next to each other and form like a little pseudo bond. Not really a bond, but they can be sort of just like for the reason that magnets are attracted to each other. Magnets don't form bonds, but they're attracted because of opposite charges. You can have the same thing, and that's what holds water together. That's why liquid water, for example, when you hold it, that's what is happening. You've got this little area of attraction between the oxygen and the hydrogen parts of separate water molecules. Now, if we can supply enough energy, like heat, to that, and spread that out, and give the molecules more energy than what can hold them together, then they'll separate and they'll turn into a gas. That's boiling water. Okay, that's how we can do it. Some things, however, don't have those polar regions. Things like kerosene or gasoline. They don't have partial negative, partial positive parts on them. It's perfectly even in all those molecules. Say this is a gasoline molecule. In octane, all of the bonds are equally shared in the whole molecule. There's no polar regions. Same thing with this one. So when you bump them together, there's nothing holding them together, really. They don't position themselves next to each other very well at all. So that's why, with very, very little effort, not even using heat, I could open a container of gasoline and it would all evaporate away very quickly, right? Because they separate out from each other. There's nothing holding them together. Between those molecules, there's no forces that are wanting them to stay together like there is in water. So by understanding polarity, we can understand, for example, why gasoline evaporates so quickly, why alcohol evaporates so quickly, why it's so volatile, why it becomes so dangerous so quickly compared to things like water and other things. So we have to understand polarity, we have to understand three-dimensional shapes and all that kind of stuff. It all works together. So take a look. Before I set this up, I want to go through one more analogy with you. If I had a ball with 2 chains coming off of it, okay, and I put that ball, let's say, right here on this table, okay, and I grabbed one of the chains and I stood about this far away from it, and whoever over here actually had the other chain. She was standing right across from me, and we made sure that we kept this chain right level with the ball on the table. Okay, if we both then we started from the same distance, everything was even and distributed, and we both took the exact same amount and size of step backwards, and we kept walking backwards at the same pace. What would happen to that ball? Would it move in one direction or the other, or would it just stay suspended where it's at? Which one would happen? Just imagine, I've got a chain or rope on that side, I've got a chain or rope on this side, we're right across from each other, and we just keep walking backward. What's going to happen? Okay, it's going to go up, but more importantly, what I'm looking at here is, will it go in either direction? Will it go that way, or will it go this way, or will it just stay where it's at? We're evenly apart from each other, we're the same distance, we take the exact same size steps and pull with the exact same size force, and we're just keep moving apart from each other. We are creating tension in the rope or the chain. It'll rise up like you say, right? But it should not move either this way or that way. Because at the same point, assuming we're the same strength, when we get here and we've reached the end as far as we can go, now we're creating tension. We can't move any farther, and the ball's sitting there. We're both pulling with the same strength, right? All right. However, think about this. What if we started like that, I was right here, but instead of her being straight across from me, she was over there where she's sitting. She's at that angle, and we're just like this. So we're sort of like a bent nature. Okay? Now, in this case, imagine that ball now being suspended between us over there where it started. But I'm starting over here, she's starting over there, and she wants to move straight out that direction, like the way the table's going. Okay? She's going to want to move that direction. I'm going to want to go straight back. What's the path of the ball going to be? Think about it. Which way is the ball going to move? I need you to understand this, or you're not going to understand what I'm getting ready to say. We got a ball in the middle. I've got a rope I'm pulling it with. She's got a rope she's pulling it with. She's going that way, straight that way, like where the table's pointing. I'm going straight back this way. We're like in a 90-degree angle, we'll say, with each other. Okay? I'm going this way. She's going that way. The ball's in the corner. Okay? And we take off walking in I go this way, you go that way. Which way is the ball going to go? It's going to split the difference, right? It's going to be like at a 45-degree angle. It's going to go right between us. All right? If I have a ball in the middle and I'm right here, and we slice in equal thirds, 120 degrees between us. One person goes that way, one person goes that way, I go this way. Is the ball going to move in any certain direction, assuming the same force is applied? Okay, no. Now, take that and add to that the fact that it's not just... So you see now where the atoms are relative to each other. If we're talking about electrons pull, okay, the same thing works. Where we are relative to each other is very important in determining where the net force ends up going, right? Where this ball ends up traveling. So position becomes very important. Not only position, but strength now. Because if I was pulling in this direction, okay, and she was pulling in that direction, but she's stronger than me, that's going to make a difference. Because the ball's not going to just split the difference anymore. It could actually go somewhere between us, but more towards her than it would me, right? Because she's pulling harder. It's going to go farther in her direction. So we got to add to not only the position of things and where that force is being pulled, but also who's pulling harder. So we got both of these things to deal with, and that's why 3 dimensions, we have to think in 3D. That's what the point of all this bond angle stuff is. We've got 3 dimensions, and we've got numbers now, relative numbers of force that we can compare who's pulling harder. So let's take a look at this. Look at the water. Look at this water molecule. This is if you look at water, you should be able to come up with this structure. You can write. You know how many valence electrons oxygen and hydrogen have. You should be able to write the Lewis structure at this point. Once you write the Lewis structure, you should be able to, in your head then, look at where your lone pairs are, where your bonding pairs are, and figure out what the 3D shape of water would be. Water would be bent. It would not be linear. On your paper, it looks linear, right? But whenever you think of it in 3D and consider where your pairs are and stuff like that, it's going to be, the electron geometry is going to be tetrahedral. But when you take away those 2 non-bonding sets of electrons and only look at what you can see, you see a bent molecule. You see water. Okay. There it is. Now, because it's bent, that actually is extremely important in terms of how it behaves. Because look what happens because it's bent. Oxygen and hydrogen. When I look at the electronegativities difference between them, I will see that oxygen and hydrogen can create a polar covalent bond. Okay? They will share, but oxygen will pull much harder than what hydrogen will. Okay, if I know that's true, it's just like the ball example that I told you. Imagine oxygen pulling more of the electrons towards itself. Pulling more than from this side towards itself. It's sort of like the force is being applied this way, the force is being applied this way. So if we're looking at this in terms of movement like we were with the ball, which way would the ball move if the oxygen was a ball? It would go up in this direction, right? It's like someone's pushing from this side, someone's pushing from this side, and you would get a net movement in that direction. Okay? Now, this plays out in terms of electronegativity, because what this means is that water molecule itself is polar. And the reason that it's polar is because oxygen is pulling it this way, right? Creating that red line that you see. It's kind of pointed in that direction. This becomes a negative area because of all the electrons moving that way. And this becomes a positive type of area over here. That's why we have distinguishable regions now that are partial positive, partial negative for the whole molecule. This end of the molecule is partial negative, and these ends are partial positive. These polar bonds, because of the geometry there and the way that they're being pulled, result in a leftover force in this direction, so you have polarity as a result of that. Take a look over here how it's different. With CO2, when you draw it out and draw the Lewis structure, you'll see this right here with all the blue stuff that you see. Now, when you actually translate this into 3 dimensions, it still stays linear, right? Because there's no other free pairs up here affecting anything. So you got a linear. Now, if you look at carbon and oxygen, you will see that the difference in pull between carbon and oxygen is still enough to where it creates a polar bond. In other words, that bond itself, just looking at carbon and oxygen, you will see that oxygen pulls more than carbon does, to a point where you could say that a carbon and an oxygen bond is actually a polar bond. There's a lopsided bond. However, look what happens. If I straddle that carbon with oxygens, and I put them on both sides, even though I know that this oxygen is pulling that way, and this oxygen is pulling electrons that way, guess what? Since they're straight apart from each other, they balance each other out. It's sort of like when I said that first one with the ball in the middle. If we're both pulling with the same strength, that ball stays there, right? It doesn't move in one direction or the other. Same thing applies here. Even though these bonds are polar bonds, this one and this one, because of the distribution, because of the geometry of our molecule, they cancel each other out because they're directly across from each other. So, as a result, you don't get an entire molecule that's polar. Polar can be attributed to either bonds or the entire molecule. You can have polar bonds like this and still have a non-polar molecule as a whole. Okay? A molecule where you can't identify a positive and negative end like you can over here, because this is all pointing in a direction that can be summed up in this direction. Here, everything's balanced out. Questions about this? Okay, then. Carbon tetrachloride. Check this out. Okay, you've got up here a carbon in the middle, and you've got chlorines coming off in all 4 directions in a tetrahedral shape. If you look at carbon and chlorine, you will find that chlorine has a pretty good pull. Okay, you can create a polar bond between carbon and chlorine. However, just because you've got a polar bond with carbon and chlorine, you got to realize that we've got more than one bond in our molecule. We've got to look at all the bonds that we have and see how they're distributed. So, if I have chlorine and I've got carbon in the middle, what I have is more pull from chlorine pulling on carbon. But the thing is, all of these chlorines are spaced out equally in all 4 corners from each other, spread out equally. They're all pulling with the same force. So they cancel each other out. It's almost like if they were pulling a ball, it would just stay hanging right in the middle. It would just be suspended there. Okay? Well, we think about electron pull forces the same way. If they're all pulling in the same directions, the net force is 0. It all balances out. So in this case, this is a non-polar molecule, even though each one of these bonds are polar, because it all balances out. However, if you have CH2Cl2, that's different, because you still have a tetrahedral shape, but the pulls are going to be different. Because if you look at carbon and hydrogen, carbon will pull more than hydrogen does. You can create polarity between carbon and hydrogen, and notice the arrows are going towards carbon. That means it's carbon's pulling more, okay, pulling it towards itself. However, when you look at chlorine, chlorine actually pulls away from carbon. It pulls more towards itself. So if I've got arrows going towards chlorine, electron pull going towards that chlorine, electron pull going that direction and that direction. Look how all those arrows are pointing, and imagine them all being pulled at the same time. This is not balanced out at all. If you would see this arrow represents the sum. After you put them all together, what direction would it move? You could see that you could split the difference right between them. And if I had to draw an arrow that represents like motion in this case, if it was force, it would go somewhere in this direction, right? It would move up. The only way you're going to balance this is if they're all pulled apart in opposite directions, balancing everything out. Here, you end up with polarity. This region over here, where the electrons are moving towards, all this over here will be a partial negative region because that's where the electrons are going. This will be your partial positive over here. I know that we're rounding out our hour here, but I'd just as soon finish this so we can be done with it because this is the last thing that we're going to do. The ultimate question here is, here's the distribution of forces, right? If I have balanced forces on both sides, I'm going to get nonpolar. Here, you can see that it's not balanced. It will end up going like in this direction if it was moving. This is polar. This would be nonpolar. Everything's balanced out. Again, nonpolar. You can see here that this would be polar. It's not balanced. Okay. Now, the ultimate question is then, you have to know a lot of things to answer this. I can ask you one question. Okay? And the question would be something similar to, if you have ammonia as a molecule, is ammonia a polar molecule? And you have to answer a lot of questions to do this. You have to, this incorporates the stuff. Pretty much everything we've done in this chapter leads up to this type of question. Okay? Determining whether or not a molecule is polar. All right. What you're going to want to do is, this is not really going to help, so you can look at that yourself if you want. The first thing that you want to do when you're determining polarity, write your Lewis structure. So the first thing that you're going to want to do is figure out a way that these things are going to be located relative to one another. I went in class, I talked about some hints. How did I do that? You want to look for your most metallic element and put it in the center. And your hydrogens and your halogens are all going to be around the outside, that kind of thing. Okay? So put that nitrogen in the middle, put the hydrogens around it, connect the dots. Okay? Tie them together. No dots here, I guess, yet. But tie them together. And just remember that every time you draw a line, that represents shared electrons. Okay? All right, so there's what we've got so far. We figured out that much of it. Next thing you got to do is figure out, to draw your structure, how many valence electrons each one of them are bringing to the table so you can make your valence electron bank. Okay? So we know that every nitrogen that we're going to use has 5 valence electrons. Every hydrogen that we have is 1. Add those up, considering what we have, and you'll see that by the time this is over, you have to account for 8 valence electrons in your overall Lewis structure. All right? So then I said start from the outside in and fill them in. Now notice, out of the 8 that we're allowed to use, we've already used 6 of them. Right? So we only have 2 dots, 2 electrons that we have that we can possibly write into this structure somewhere. So we start on the outside, the ones on the end, and work our way in. Do we need to add anything to these hydrogens? No. They all have 2. They're all happy. Remember, hydrogen's happy with 2. All right, that means we've got 2 electrons now, and the last place to put them is going to be on the nitrogen. So we put 2 dots up here. There you go. You've got your Lewis structure so long as everything adds up. Let's look and see. 2, 4, 6, 8. That's how many valence electrons I needed. I'm accounted for. I've got all hydrogens happy with 2. I've got a nitrogen happy with 2, 4, 6, 8. We're good. That's my Lewis structure. Now, we take it a step farther and realize imagine this model in your head now. I've got a nitrogen with 3 hydrogens stuck on it, but what else do I have? I've got a lone pair of electrons on top, right? So now you can see how my shape is not going to be just 120-degree angles like you would think with 3 things sticking off. It's going to be this. Okay, what is the electron geometry? What's the molecular geometry? Trigonal pyramidal. So this will be trigonal pyramidal in shape. Okay, so I'm going to take this off so it doesn't confuse you. I'm looking at this. Okay, it's suspended. Now you can see what's going to play out here. To determine whether or not this ammonia is going to be polar, what I have to do is see how the forces are distributed throughout it in terms of electron pull. See how it's lopsided, right? If it was flat like this and everything was pulling in different directions, it could have a better chance of being balanced. Like this, if, for example, nitrogen pulls more and they're all pulling up in that direction, it's sort of like, imagine if I was pulling it, it would sort of, rise up like this because they're all pointing up and towards the center. If they're all pointing away and down, I would get a net resultant, called in physics a resultant vector is what we would call this. After you sum up all the forces, it would sort of, imagine it going down or whatever. You've got this. So let's look and see. Now what we have to look at is, this is nice and simple because we only have one type of bond. We have a nitrogen-hydrogen bond. Okay? So all three of these bonds that we're looking at here are nitrogen-hydrogen bonds. All right, so we want to look on our table now and see what the difference in pull is between a nitrogen and a hydrogen. And you will see that nitrogen is 3, a hydrogen is 2.1 on the electronegativity table. And you will see that's a difference of 0.9. It's a polar covalent bond. What that tells you is, notice which one's bigger. Nitrogen's bigger. That means when I have this setup just like this, I have nitrogen pulling these electrons closer to itself and harder than what hydrogen is pulling. So I'm sort of like I'm moving all in towards the center, up and towards the center with my electron pull in this particular scenario. So we have a polar covalent bond. Now if it was ionic, what would happen is, this would be completely separate, and you would have like what you normally would have with a sodium, like sodium chloride, something like that, two distinct separations that pulled apart. Here it's a polar covalent. It's lopsided sharing is what's happening. Okay. Now what I need to do then is imagine this in 3 dimensions, like you see here, like you see here as well. And if I know that the nitrogen pulls more than the hydrogen, is this all balanced out? Looking at my shape. Let's say black is nitrogen and white is hydrogen. If the nitrogen is pulling all the hydrogens towards itself, is this all balanced out? Think about it. Think of a force going that way and up, a force going that way and up, and a force going this way and up, and say it was a force of motion. Someone was pushing that way, and that way. Which way would that black ball go? Imagine a ball hanging from the ceiling above your head. 3 of you were 120 degrees apart from each other, we'll say. You have 3 of you spread out, a ball right here, and you all push with the same amount of force at the same time. Which way is that ball going to go? Well, it's above you in this case. Think about it. Just think. Don't think too hard. Just put yourself in this position. Hang a ball right here. We're going to be the hydrogens. Me and 2 of you lucky winners are going to be the hydrogens here. This black ball right here is going to be the ball that's hanging from the ceiling. Okay, it's going to be hanging about right here, otherwise I won't be able to reach it. If we're hanging about right here, and Brad stands there, I stand here, Natalie stands over here, we're exactly spaced out from each other like you would see here. Okay, perfectly spaced out, and that ball's right where we can all reach it. We're all the same height, we're all the same strength, and right in front of us we start to push. What's going to happen to that ball? It's going to go up, right? It's going to raise up a little bit. Same situation applies here. Okay, I've got force going that way and up, just like I would have pushed. This way and up, moving towards the ball, right? Like Natalie would have pushed. This way and going up like Brad would have pushed. The same sort of thing, except instead of a pushing force, I've got a pulling force here with this center thing. So as a result, my net force, what's left over, is in this direction. Okay. So my question then is that going to be polar? Remember, polar means it's not balanced. Non-polar is it is balanced. Is this perfectly balanced to where that ball would not move? No, it is not. So is this polar or non-polar? Polar. Okay. That's how we figure out if something is polar or not. There's a lot to it. Here in this case, you see the arrows. Okay, that's the force. It's a trigonal pyramidal shape. The bonds are polar, so that means you got to look and see which way the bonds are being pulled. So the Lewis structure is right. The bonds are polar. The shape is unsymmetrical. It's not all balanced out, so therefore your molecule should be polar. You should end up with a polar molecule for NH3. Okay? All right. That's chapter 10. Probably the easiest chapter we've done.